If you were to take a moment to consider all the absolutely essential elements for sustaining life on Earth, you'd realize that oxygen is, by far, the most important of them all. Today, oxygen is an essential element in many industrial applications and manufacturing processes, such as medical and military operations, mining, pulp and paper, water treatments, and aquaculture. A key to running a successful operation in these industries is to always have accessible, concentrated oxygen. It is essential for hospitals treating patients to have pure oxygen ready to use for operations. Mining requires the use of oxygen not only to help workers breathe in underground locations, but to be used in oxidation to help maximize the output of metals and minerals. In aquaculture, oxygen is used both in recirculating aquaculture systems and net pen systems to assure a comfortable and healthy environment for fish to develop and grow in. One major reason that companies in these industries do not take full advantage of the benefits of oxygen concentrators centers around not being able to produce oxygen at a specific purity on location for a cheap enough price. While other oxygen processes can and are still being used, such as liquid oxygen supplementation and pressure swing adsorption, both of these can be costly. Oxygen Solutions specializes on manufacturing machines that use the vacuum swing adsorption process, which can save on maintenance and operating costs while producing a high-purity oxygen for industry applications. So let's talk about adsorption and what it means. And no, while it sounds a lot like absorption, they mean two different things. Absorption is the process where molecules enter a bulk phase, either in liquid or solid state. The best way to demonstrate this process would be to soak water into a sponge. The molecular structure of both the sponge and the water stays separate, but stay combined into one solid object. In the absorption process, the objects can easily be separated. The water can easily be separated from a sponge by squeezing the water out. Adsorption, however, is to bind or attract certain molecules to gather and remain on a solid surface. The molecules will stick to the surface of the solid, but they will not combine with the surface. Once the molecules are caught, they can be removed and filtered out. A good way to think about this is to compare it to a face mask. When wearing a mask, you want to filter out the harmful chemicals in the air. When breathing in, a filter will absorb those harmful chemicals while allowing clean air to pass through. The undesired molecules will stick to the filter so you don't breathe them in. When you're done with the mask, the chemicals can be cleaned or treated to remove them. The adsorption process comes in handy when it comes to thinking about concentrating oxygen remotely. To make concentrated oxygen, you'd need to be able to separate it from the air that we breathe. Breathable air is about 78% nitrogen, 21% oxygen, and about 1 to 2% of other elements such as carbon dioxide. Two issues can occur here. One, you'd need an effective and absorbent surface to capture the nitrogen in order to produce a purer oxygen. Second, consider that as a state of matter, gas molecules tend to move fast and randomly. As such, you'd need a highly effective material to catch the desired molecules. In nitrogen-oxygen separation, a material called zeolite, which is highly attracted to nitrogen gas, is used. By capturing the nitrogen, the result is a higher concentration of oxygen gas. Now with the right materials, all that's needed is the process. There are two industry processes commonly used to accomplish oxygen concentration. The first is called pressure swing adsorption. The idea behind it is that if you put gas molecules under enough pressure and force them to stay together, the gas molecules will be attracted to solid surfaces. The higher the pressure, the more molecules you can force to adsorb onto the solid surface. Once the desired gas is filtered out, depressurizing the concentrator will release the molecules stuck to the adsorbable solid surface. Basically, you're using pressure to attract the molecules and releasing the pressure to clean off the solid plate they were stuck to. In nitrogen-oxygen applications, natural air would be sucked into the air compressor. From there, the air would be pressurized to around 4 to 8 bar. To put it into perspective, 4 to 8 bar is around 400 kPa to 800 kPa. The air pressure at sea level is 101 kPa, and that's 4 times the normal air pressure we experience on land. To get to 400 kPa naturally, you would have to swim around 40 meters under the surface of the ocean. Under pressure, the zeolite would attract the nitrogen to its surface and allow the oxygen and argon to pass through. Once the oxygen had been separated from the air, the pressure would be released to normal atmospheric levels and the nitrogen would detach from the zeolite. The amount of pressure placed on the air in the compressor would determine the purity of the oxygen produced. As such, the pressuring process is both the means to force the nitrogen to stick to the zeolite plate and the means to clean off the plate once the air is separated. While an effective process, the trouble behind using pressure swing adsorption is that it consistently needs a high amount of energy to compress and decompress the gas, which can be costly depending on the amount and purity of oxygen required. High energy usage means high energy cost. Also, consider that consistently subjecting zeolite plates to high amounts of pressure means that the equipment will need higher amounts of maintenance and regular replacements, all of which costs money. The second industry process is called vacuum swing adsorption. While like pressure swing adsorption in that it uses zeolite, it is more cost-effective in comparison as it uses less energy and requires less maintenance to produce an equal oxygen output. The main difference between the processes is that while pressure swing adsorption uses pressure to clean off the zeolite plate, vacuum swing adsorption uses a vacuum process. Remember that as a state, gases like to move and occupy space whenever possible. Think of your favorite space movie. When a hole is blown into the side of a spacecraft, everyone and everything in that room will be sucked into space. Why? Well, space is just as it's named, space. Space doesn't have any gases floating around like on Earth. Spaceships are concentrated little containers full of compressed, trapped gas. When a hole is made in that container, that gas now has a lot of space to expand into. In this case, space is a vacuum and sucks out the oxygen from the spacecraft. It is the same vacuum process that vacuum swing adsorption uses to clean off the zeolite plate. Vacuum swing adsorption uses a blower instead of an air compressor. An air compressor forces concentrated air at high speeds through a hose. A blower works by blowing force air at a high velocity. Its job is to make positive pressure above the vacuum or the atmospheric pressure. The big difference between the two is that air compressors operate at high pressure ratios, while blowers operate at low pressure ratios. As such, the need for all the equipment such as a dryer, a filter, and a buffer tank in pressure swing adsorption is eliminated, and less energy is needed as a result. The air is forced into a slightly higher than normal pressure state of 1.25 to 1.5 bar, or around 125 to 150 kPa. The nitrogen will adhere to the zeolite, and the oxygen will continue to pass through at this pressure. Once the oxygen has passed, a vacuum state will be created. The vacuum state will release all the nitrogen off of the zeolite plate and reset the concentrator to restart the process. What's great about this process is it eliminates the need to keep a constant high-low pressure to produce the same quality of oxygen, which lowers overall operational and maintenance costs. The vacuum swing adsorption process is made viable by using lithium exchange to zeolites. This means that there is a further guard to the zeolite, which means it has a higher nitrogen capacity at lower pressure. While lithium exchange zeolite is more expensive than the zeolite used in a pressure swing adsorption system, the lithium exchange zeolite does not need to be replaced as frequently, in part due to its durability and due to its lack of subjection to pressure change, which saves money on maintenance costs. If visualized on a scale, zeolite is kept at a state of 101 kPa, which is a natural atmospheric pressure. In pressure swing adsorption, the zeolite is forced to the 400 to 800 kPa levels, keeping it under pressure and cleaning the plate off in the process. Vacuum swing adsorption works the other way. It keeps the zeolite at natural atmospheric pressure and then creating a vacuum state of 50 to 60 kPa to clean off the plate. Creating a vacuum environment is less harmful on a zeolite plate, meaning there won't be a worry of needing to maintain or replace the plates as frequently. Oxygen Solutions has developed a vacuum swing adsorption process that was designed for the modular, low-maintenance, low-cost, and simpler production of high-purity oxygen. As such, many industries have applied our technology to their operations and applications. Vacuum swing adsorption lowers the cost of oxygen concentration, making it more affordable. Also, due to the simplicity of the technology, it can be moved to more remote locations than ever before. Having a reliable vacuum swing adsorption oxygen concentrator that is low maintenance will result in lower energy costs, will last for years, and will revolutionize any operation. If you want to improve day-to-day operations, decrease operational costs, or learn more about our cutting-edge technology, contact us on our website or check us out on our social media pages for up-to-date information.